Hello students, welcome back. As a final video lesson of Module 5, we'll study an optional topic. We will prove the chain rule. More precisely speaking, we'll go over a naive justification of the chain rule. Maybe a bit too modest, but I cannot use the term proof or even sketch of proof because there's a bit of an issue related to this computation down here. In Calculus 1 level, of course, this will pass on as a full proof, but there's a bit of an issue. Okay, let's begin. Let's begin from the definition of the derivative. One way to define a derivative is through this limit. Another way to define it is through this limit. These two are equivalent. All we have to do is to take h is equal to b minus a, and consequently b is equal to a plus h, and then we get the second expression. These two are equivalent. In this particular case, we are not going to use this one, so I de-emphasize it in gray. We're going to be using this one. Okay, let's go. This is how we explained the derivative graphically in Module 3, and here's a reminder. This quantity here, without the limit, this quantity here is actually a rise of a run, a slope of secant line, as you can see in this picture, the first picture, the difference of y coordinate over difference of x coordinate. Now what about this limit? That's explained by the second picture. This green point b is approaching to the red point a, as you see here, and you can clearly see that green secant lines are converging into the red tangent line. The result, we get the derivative, the slope of tangent line, or the instantaneous rate of change. Okay, that was a quick reminder, and let's go. That's the definition of the derivative. We're going to have to use it multiple times here in this proof. Okay, here we go. In this definition of the derivative, let's write capital F as composite function f circle g, or equivalently f of g. Then what do we get? We get the first line. Compare this first line with the definition. Exactly the same, except for, of course, the choice of characters. Instead of capital F, we get f circle g, or equivalently f of g. Now let's divide and multiply by the same quantity, g of b minus g of a. Essentially, we just multiplied by 1, so I didn't change anything. Consequently, the second line is the same as the first line. There's a bit of an issue, but we're going to come back and do it a bit later, after finishing this initially. Next, from the second line, we have this fraction and that fraction multiplied together, and provided that both fractions converge to a certain limit, we can use the limit rule. Limit of the first fraction times the limit of the second fraction. Just a limit rule. Now, the second limit is a little bit easier, so let's do that first. Compare this expression with that expression. What's the difference? Capital F of b minus capital F of a over b minus a. G of b minus g of a over b minus a. What's the difference? Exactly the same, except, of course, for the choice of character. So the first is capital F prime of a. The second must be g prime of a. So it's just a definition of the derivative used for the second time. Alright. Now let's go over to the first limit. This is a little bit trickier, so I use a bit of color coding there. A bit too complicated, so I'm reducing this using appropriate substitution. Let's call alpha as g of a and beta as g of b. Color coding will help you see it better. Then this g of b will become beta. This g of a will become alpha. Consequently, this fraction and that fraction become the same. They all follow from here. Do you see? This and that are the same because of this. Now there's a bit of an issue here. Limit b is approaching to a versus limit beta is approaching to alpha. Let's postpone that. And let's look at this limit. What is this? This is precisely the same as this limit expression or that limit expression, except of course for the choice of characters. Here g, so we have g prime. Here we have f, so we have f prime. And then we have capital F there. And these characters there, those are a, so we have capital F prime of a. We have this a here, so g prime of a. No longer a, those are alpha, so we have f prime of alpha. And then please remind yourself what is alpha? Alpha is g of a. So rewrite this alpha into g of a. And finally, we get what we want. Please compare the last line with the right-hand side of the original statement. They are exactly the same, except, of course, the choice of character. In Calculus 1 level, this is perfect proof. Completely fine. Now let's go a little bit deeper, because there are a couple of issues here. Issue number 1, this one, g of b minus g of a. What if this is 0? If this is non-zero, then you can divide and multiply by the same thing and consequently multiply by 1, so the second line is valid. But if this is 0, then everything goes down. How do we avoid it? Well, if we have just finitely many zeros there, g of b minus g of a is equal to 0 only 15,000 times. In that case, you can get b close enough to a bypassing all 15,000, and then from that point on, no more zeros, so it'll work smoothly from this point on. No problem there. Any finite number is going to be okay. Now, if g of b and g of a are the same all the time, in other words, this quantity is 0 constantly, in that case, g is a constant function, so g prime of x is constantly 0, and this entire thing is just 0 equal to 0. No problem there either. Potential problem rises when this quantity, g of b minus g of a, is equal to 0 infinitely many times, but not constantly 0. So g of a and g of b are the same infinitely many times, but not always the same. That could cause a bit of a problem, but oh my, that's way beyond calculus level, so we are not going to worry about it. Even in real analysis 1, I'm not so sure whether we are going to deal with that. There's a way to bypass that, of course, and it is possible to express this whole thing without any denominator at all, and that's something what we are going to do in multivariable calculus and then in upper level analysis course. But in calculus 1 level, this is perfectly fine and we'll take it for granted. The next issue is this one. This limit becoming that limit. Limit b is approaching to a versus limit beta is approaching to alpha. Please allow me to remind you again. Alpha is g of a and beta is g of b. Consequently, this expression, f of g of b minus f of g of a over g of b minus g of a is equivalent to this expression, f of beta minus f of alpha over beta minus alpha. That's okay. This is equal to that because of the substitution. That's clear. But this limit, b is approaching to a, is becoming limit beta is approaching to alpha, is not that clear, but it is something we can do in calculus level. How? You have to look at the continuity of g. Basically, this is what happens here. G is continuous. You see, in order to have this, g has to be differentiable. Every differentiable function is continuous, so you have to have continuity. Yes, because of the continuity, we'll have this. b is approaching to a means function value g of b approaching to g of a, which means beta is approaching to alpha. That's the key. So limit b is approaching to a implies beta is approaching to alpha because of this arrangement, which follows from the continuity of g. That was the second issue. First issue here, second issue transition from this limit to that limit. Otherwise, everything is fine in this proof. Now, how do you take care of this? It's coming from the continuity, so we actually handled it. Even in calculus level, we could do it. How do we take care of this? That's a different issue. One way to do it is to rewrite this differentiability and chain rule and everything without denominator at all, and you can do an alternative proof like that. It's much more advanced, but it is possible, and that's something we are going to do in multivariable calculus and then in multivariable analysis as well. For now, let's keep this as the proof or a sketch of proof, or if you're a purist like me, a naive justification of the chain rule.